continue on the density of states, and I want to apply it to a test case and see how well that works. This is work done with my student Tobias Hundisbacher, who's here, and by the way, Tobias is finishing his PhD very soon, and he's looking for a postdoc. So we're going to have a look at the Ising model again. Why? So this is the partition function of the Ising model with the nearest number of ferromagnetic interaction and the external field term. And I'm going to make the external magnetic field H pure imaginary. And why is that interesting in our present context? Because it makes the action complex. So there's going to be a weight factor which is complex here, where m is the magnetization. So it's a simple model with a severe sign problem. Sign problem is particularly severe because when H is pure imaginary, then the whole partition function here may vanish, and then you have new types of thermodynamic singularities that we're going to see. So there's a combination of a benchmark for sign problem, interesting critical phenomena, and also I discovered by literature search that this problem had been barely studied just by a single person by Monte Carlo methods. So again, this is the partition function. If you define these variables x and y, then up to some prefactor, the partition function is a polynomial in x and y, so it will have zeros in the complex x plane or in the complex y plane. These zeros of the partition function in complex x are called Fisher zeros, and in complex y are called Lee-Yang zeros. And then we're going to be interested in the Lee-Yang zeros. And Lee and Yang, a long time ago, showed that these zeros in y are on the unit circle, which is another way to state that the zeros occur when H is pure imaginary, or zero. And moreover, the Lee-Yang theorem says that above the Curie temperature in the high temperature disordered phase, actually Lee-Yang zeros accumulate along some H singularity. And we're going to see what that means. Moreover, Fisher, 20 years later, explained that this H singularity, where zeros accumulate, can be interpreted as a second order phase transition, and the universality class is that of a scalar field theory with interaction I phi cube. So I phi cube sounds a little bit strange, but in fact, it's one of the examples of a PT symmetric theory dear to Carl Bender. So it's not that exotic. You would think that the action is unbounded, but this, when you take this factor in the exponent, the magnitude of the weight remains bounded. It's bounded by 1. So actually the whole theory can be studied. So what do these Lee-Yang zeros give you? So let's look at the phase diagram of the Ising model. This is what you should be careful where I stand. This is the usual phase diagram when you consider a real magnetic field. So this red segment represents a first order phase transition, and it ends with a second order critical point at the Curie temperature. This is the well-known phase diagram, but now, since we're making H complex, let's look at the imaginary direction for H. And then this is the corresponding phase diagram. So you have this H equals 0 segment, which is there as before. But now, if you go at temperatures higher than Tc, then this line bifurcates into this pair of complex conjugate dotted lines, and these are the so-called H singularities. So what that means is that inside this domain between the dotted lines, the partition function has no zeros, and then zeros accumulate along these dotted lines. And I want to draw your attention to the similarity with QCD. This is the putative phase diagram of QCD, so for real chemical potential and temperature. with a first order line ending with a critical point, similar to that. And, and this is taken from a very interesting paper by Misha Stefanov, and that represents the singularities of the partition function in the complex mu square plane. So I want to draw your attention to the similarity between these red dotted lines and these red lines here. So at low temperature, if we increase the chemical potential, we have a singularity along the real mu direction here, and in the mu square plane, that corresponds to a singularity here along real positive mu square. And now, as we increase the temperature, the singularity moves to smaller mu, and when we reach the critical point here, the singularity bifurcates into the complex plane. And these lines here are the analogs of these edge singularities there. So maybe we can learn something by studying more closely this Ising model. So I haven't mentioned the number of dimensions yet, but in one dimension you have a spin chain, and then your Ising model is, in the absence of external field, is always disordered at any temperature. So Tc, the critical temperature, is 0, and the phase diagram is modified to something like this. At any non-zero temperature, you will have a phase where there are no zeros and then edge singularities. So it's analytically solvable, so it's a good benchmark problem to compare Monte Carlo with exact results. In 2 dimensions, you know the critical exponents as you approach these lines, and it's very interesting work, and you can try Monte Carlo, and in more than 2 dimensions, essentially nothing has been done yet. So, we're going to stay in 1 dimension, just a spin chain with an imaginary external field. So you can solve that 1-dimensional model using a transfer matrix. So this is the transfer matrix connecting one spin with its neighbor along the chain. These are the matrix elements. You can diagonalize this matrix and compute the partition function, and then look in the, so instead of temperature, this is the inverse temperature, and this is the imaginary external field, and red means positive Z, blue means negative. So of course between red and blue there's a line of zeros here. So you see this is for increasing system sizes. You see what I said just before. There's a region where the partition function is positive, everything behaves the usual way, and the 2 eigenvalues, number 1 and number 2, are both real. And then here the partition function vanishes, and above there are alternating regions and lines of zeros which become denser and denser as you make your system bigger, so the zeros accumulate in that region. And this is the edge singularity that I mentioned. And algebraically, what happens is that when you cross these edge singularities, the eigenvalues of your transfer matrix become complex. So instead of 2 real eigenvalues, you have a complex conjugate pair, and that gives rise to the possible vanishing of Z. So you really have some behavior just like at the second order phase transition. For instance, you can analytically, of course, compute the locus of this edge singularity as a function of the inverse temperature for an infinite size, and then look for the finite size corrections. So there's a pseudo-critical external field for which on the finite size the partition function will vanish, and it's displaced from the thermodynamic limit value by corrections 1 over L squared, etc. You can do all this beautiful analytic finite size scaling. And you can look at the magnetization, the expectation value of the spin itself. And when the external field is imaginary, then the magnetization also is imaginary. and as a function of the external field, it diverges when you reach this pseudo-critical value. Why? Because the denominator in this expectation value is the partition function, and the partition function vanishes. So the ratio diverges. So this is what you obtain analytically on systems of increasing size. The magnetization, imaginary magnetization, as a function of the external imaginary field, and it's on a log scale because it increases dramatically and diverges here when you reach the first zero of the partition function, the H singularity. So we want to, and then you see the accumulation of zeros as you increase the system size, the wiggles become denser and denser. So we want to look at this quantity, the magnetization by Monte Carlo, and we're going to use the density of state method. And I want to call your attention to all the work. So the first work where this method is applied to QCD that I know of is by Andreas Boch, 30 years almost ago. And he himself cites Hammersley and Hanscom, the Bible of Monte Carlo in the last millennium. And in those days, this was called stratified sampling because you divide your Hilbert space into layers of constant, in this case, constant magnetization. So it's a really old method. The LLR improvement is very interesting when you have a continuous spectrum, but here in the Ising model, the spectrum is discrete, so there's no, it's not a place where to apply the LLR method. We can use the ordinary density of states method, whereby we rewrite the partition function here as a sum over sectors of different magnetization. So we insert this delta here, and each sector is weighted by this phase factor, and what's in the brackets are now called the density of state rho of m, where m is the magnetization. So, and now the task is to numerically determine rho of m, and the way it is done is by running independent Monte Carlo simulations, which are restricted to sampling neighboring sectors of m. M is even, of course. If you flip one spin, you change the magnetization by 2. So the relevant ratio to measure is the ratio of densities of state for m and m minus 2. And these ratios can be measured by Monte Carlo. The system is at a high temperature, so an ordinary single spin metropolis is perfectly adequate, and you obtain these ratios with a relative accuracy which is independent of the value of n. And that's what LLR collaboration calls exponential error suppression. You can, this is the result as a function of m, that this is rho, the density of states on a log scale. So you see again this dramatic dynamic range. And when you do this Monte Carlo sampling, the relative accuracy here on these very rare states is just as good as in the middle. So that's what's called exponential error suppression, and it expresses the fact that the overlap problem has been solved. Think of the sector here of maximum magnetization. That means all spins are up. There's only one state here, in compared to an exponential number of states there, and you can determine this density of states with uniform relative accuracy across the whole interval. Moreover, you know that there's only one state here, so the normalization of your partition function is fixed, and you can compare this sum here to exact results for the Ising model. Everything works well. Now, as Biagio said, well, you're not done. This is the easy part. Once you have rho of m, then you need to Fourier transform to obtain the partition function in the presence of this external imaginary field. And that's where the sign problem strikes you. So our observable of choice is going to be the magnetization as a function of the imaginary external field. And I showed you these results before. It starts at 0, and then the exact result is the sign, and it diverges when you reach the H singularity. And this is an example of a Monte Carlo So you see that even though the system is small, the task is difficult. So I want to look at these two questions. What is the computer effort required to go to determine this magnetization for larger h, I? And how does the computer effort grow as I increase my system size? So let's first try to go on a fixed system. I fix the temperature, I fix the system size, and I increase the statistics by 6 orders of magnitude between here and there. And this is the result that I obtain for my magnetization. So you see that the crucial point here is as I increase my statistics by a factor 100, the maximum value of h that I can probe increases by a constant, which is about 0.5 in this case. So 0.25 is my maximum here, goes to 0.3, 0.35, 0.4. So clearly there's an exponential complexity. The computer effort grows exponentially as a function of the external field that I want to probe.
Sorry, Philippe, so here you're sampling from this determined role.
Yes.
Yeah, so you're not doing a numerical.
You're using my time.
It's okay. We can count.
I'll talk very slowly.
Yeah.
So you're not doing some kind of semi-analytical integration of the phase. You're really sampling.
That's coming.
Yeah.
But this plain vanilla version has an exponential complexity in the external field. But the most crucial for QCD is to go to the thermodynamic limit. So how does the effort grow with the volume? So now here I fix the relative error. It's always the same, and I increase my system size, and you see how the quality of the observable degrades. Each time I multiply my system size by 2, I have to be less ambitious and reduce my imaginary field by the same amount. So this is the evidence again of an exponential complexity, this time as a function of the volume. That's bad. That's what we wanted to fight against, and the density of states suffers just like any other method from an exponential complexity. So what can we do? Let's try to improve the situation. The first idea that we had, it was to change to dual variables. Since we've been working with worms for a long time, then let's do that here. You can rewrite your partition function in these new variables, which are k attached to links, 0 or 1 variable, and m monomers attached to sites 0 or 1 with a constraint here. And then now you have the same partition function expressed in a sum over sectors, but these are sectors of fixed monomer numbers. And you still have this equivalent of a Fourier transform, but the variables are different. What happens? So this is the density of states that I showed you before as a function of magnetization. This is, for the same system, the density of states as a function of monomer numbers. And it looks very different. But the results in the end, for same statistics, same accuracy, same computer efforts, they are almost the same. Maybe you can go to slightly larger, very slightly larger values of the imaginary field, in this case with monomers. But it's not a solution to what we want. So what LLR has been suggesting, and we're going to have a talk hopefully this afternoon on this, is to, and that's what Gert was asking about, instead of using the Monte Carlo data, the raw Monte Carlo data, let's smooth this Monte Carlo data with a clever ansatz which reduces the number of degrees of freedom but doesn't spoil the physics. And then you have to be very clever to find this ansatz. So I wasn't. I looked at this curve and said, well, it looks like a polynomial of even degree, and I fitted. So here on this figure there are actually two curves, the exact one and the fit. And you don't see the difference. But when you compute from the fit the magnetization, you get this red line, whereas the exact answer is this purple line. So you get spurious poles, you get the wrong answer. Okay, so this is not a good fit. So maybe this is the wrong function to fit. Instead of fitting the density of state, let's fit this ratio, rho of m, rho of m minus 2. And this is, again, this plot where there's the exact numbers and the fit, and there's to the naked eye there's no difference, but again when you compute the magnetization you get the wrong answer. So introducing a fit introduces a bias. You can change the fitting procedure, try to fit better the tail here. That's what I thought would work, and indeed it works a little better than there. But anyway, you lose something, you don't converge to the correct answer anymore. So my conclusions, with the zero time I have, is this Ising model with imaginary edge is fabulously interesting and hasn't really been looked at from a numerical angle before. The density of state method is from the last century, the last millennium. It's an old stuff. And here in this paper, PRL, there are results for 2 to the 4th lattice. It was not followed up by studies on larger lattice because of the complexity, which is exponential in the volume. And the LLR method provides the so-called exponential error suppression, but this is not what we want. We want to reduce the exponential complexity in terms of the volume, and we want to bypass or overcome this hurdle, and the LLR method, as far as I can tell, doesn't do it. You can try to fit, but I haven't been clever enough to find the right kind of fit without introducing a bias. And as a final remark, Biagio also mentioned this is a Fourier transform going from the density of state to the magnetization. This is, of course, very similar to QCD, where the canonical and grand canonical partition functions are related by Fourier transform in the imaginary chemical potential. Thank you very much.
We have time for maybe one question.
Well, it's maybe more as a comment. So it's clear that, as Biagio was explaining, that the sign problem, solution to the sign problem might be theory dependent. And we also felt uneasy with the fit of log rho to a polynomial, which solved the problem just for two theories, which is Z3 and heavy dense QCD. And then we introduced maybe a fit-independent approach, which is this modified cumulative expansion. So maybe that would be a way forward to...
Yes. So I was not aware of this cumulative expansion, so I didn't test it. But the first step in the cumulative expansion is to fold the theory. So here we have... Here the phase factor when h is imaginary, the phase factor goes from minus volume to plus volume, and the first step of this cumulative expansion approach is to fold this on the interval minus pi pi. And as you do that, you see that if you start with a very broad Gaussian, and you fold it to the interval minus pi pi, it's going to become extremely flat. So a priori, it makes your task much harder, intuitive. So I don't have concrete results to show testing this approach, but a priori it seems like a counterintuitive way to improve the situation, because you fold it.
Maybe a very quick question here.
Very quick. When you try this polynomial or cumulative approximation, can you observe convergence in using more and more cumulus, using more and more?
I haven't tried the cumulative expansion.
Well, the other one, the polynomial, would you test for convergence? Because it should say that actually it does not work at all.
So here I fitted with a 6-degree polynomial for a system of size 64, where there are, I think, 17 independent numbers that enter here. And M is the rho of M is an even function, and M itself takes even values from 0 to 64. Maybe there are 33 numbers.
Isn't the exact answer a 31 over 32?
Yeah. So 6 is too small.
Yeah.
32 is the whole amount of information. I didn't try anything in between, but clearly it's a trade-off between statistical and systematic error, and you can get anything you want.
I think
But
when
if you want the exact
perform,
answer-
you see no convergence. This is would be interesting.
You see improvement, but with increased statistical noise.
To stay within schedule, maybe we can postpone the classes for later. Let's take a look again. And the next and last speaker this morning is Albert Weidingers.
You put it in? Yes, that was a mistake.